The telescope that is reading the hidden language of the universe. Right now, at this very moment, there is a telescope floating in deep space, 1.5 million kilometers from Earth, doing something no instrument in human history has ever done before. It is not just looking at stars. It is not just photographing galaxies. It is doing something far more ambitious, far more unsettling, and far more important. It is trying to map the invisible. It is trying to chart the parts of the universe that produce no light, emit no radiation, and leave no direct trace, yet somehow hold everything together. The hidden skeleton. The silent architecture. The ghost structure that decides where every star, every galaxy, and every cluster of matter is allowed to exist. This telescope is called Euclid. And what it is revealing about our universe will change how we think about reality itself. What is the universe made of? Most people would say stars, planets, gas, dust. Some might say atoms and molecules. Scientists with a deeper background might say protons, neutrons, electrons, photons. But here is the uncomfortable truth. Everything you just listed, every atom, every particle, every beam of light, every star you have ever seen or imagined, makes up only about 5% of the total content of the universe. 5%. The other 95% is something else entirely. Something we cannot see. Something we cannot touch. Something we have never directly detected in any laboratory on Earth, and yet something whose presence we can feel in the structure of everything around us. 27% of the universe is what scientists call dark matter. It has mass, it has gravity. But it produces no light whatsoever. It does not absorb light. It does not reflect light. It is completely invisible to every telescope ever built, except when its gravity bends the path of light passing near it. The remaining 68% is even stranger. It is called dark energy. And it is responsible for something that should terrify you a little. It is actively pushing the universe apart. Right now. As you watch this, space itself is expanding, galaxies are drifting away from each other at accelerating speeds, and the force behind that acceleration is something we cannot see, cannot measure directly, and do not understand at all. This is the universe we live in. 95% mystery. 5% everything we know. And Euclid was built to go after those mysteries. The European Space Agency launched Euclid in the summer of 2023, sending it to a gravitationally stable point in space where the pull of Earth and the pull of the Sun balance each other out perfectly. It sits there in a kind of cosmic stillness, rotating slowly, scanning an enormous portion of the sky with extraordinary precision. Its instruments are remarkable. A visible light camera covering an area of sky equal to roughly 200 full moons in a single exposure. A near-infrared spectrometer and photometer measuring light wavelengths that the human eye cannot see. And behind all of that, computing systems capable of handling data volumes that would overwhelm most research institutions on Earth. But the hardware is not the story. The story is what Euclid is seeing, and what it is forcing scientists to reconsider. The first thing you notice when you look at Euclid's wide-field images is the sheer number of galaxies. Not dozens. Not thousands. Millions. Tens of millions. Stretched across cosmic distances so vast that the light from the most distant ones left its source before our planet even existed. But the second thing you notice, and this is the thing that stops you cold, is the pattern. They are not scattered randomly. They are not distributed evenly like points of light on a flat canvas. They are arranged. They trace lines and curves and intersections. They cluster in certain places and avoid others entirely. And when you step back and look at the largest scales, a structure emerges that looks less like a random distribution and more like something organized. Scientists call it the cosmic web. Imagine a vast three-dimensional network, like the neural connections in a brain, or like the threads of a spider's web stretched across billions of light years. Long filaments of matter stretch from node to node. Where filaments intersect, enormous clusters form, some containing thousands of galaxies packed into a single gravitational knot. And between these filaments and clusters, there are voids, regions so empty, so devoid of matter, that they seem almost deliberate in their emptiness. This is the large-scale structure of the universe. And Euclid is giving us the clearest, most detailed map of it ever produced. But here is what makes this map deeply unsettling. Most of the structure is invisible. The filaments are not made primarily of stars and gas. They are made of dark matter. The nodes are held together not mainly by the gravity of visible galaxies but by the concentrated pull of matter that produces no light. The voids are not simply empty space. They are actively shaped by forces operating in ways we are still working to understand. What we can see, every glowing galaxy, every brilliant cluster, is like foam floating on the surface of a much deeper ocean. The real structure is below, in the dark. Now let us talk about how Euclid actually detects something invisible. The technique is called gravitational lensing, and it is one of the most elegant ideas in modern science. Einstein's theory of general relativity tells us that mass warps space. Not just in a metaphorical sense, literally, physically warps the geometry of space itself. And when space is warped, light does not travel in a perfectly straight line. It follows the curve of space, which means it bends as it passes near a massive object. This bending effect is measurable. When light from a distant galaxy passes near a concentration of dark matter on its way to our telescopes, the light path curves slightly. The galaxy on the other side appears distorted, stretched, squished, or smeared into an arc. Euclid looks at the shapes of hundreds of millions of distant galaxies simultaneously. It measures those subtle distortions with extraordinary precision. And then it works backward, using the pattern of distortions to calculate where the mass must be, how much there is, and how it is distributed across cosmic scales. This is dark matter mapping. And Euclid is doing it at a scale that was previously impossible. What the maps are showing is striking. Dark matter is not smoothly spread across the universe. It is concentrated into the same filamentary web that visible matter traces, but the dark matter came first. The dark matter built the structure, and then ordinary matter fell into the gravitational wells the dark matter had already carved out. Galaxies did not build the cosmic web. The cosmic web built the galaxies. This is a fundamental reversal of the way many people intuitively think about structure in the universe. We tend to think of visible things as the active ingredients, the builders, the cause of what we observe. But Euclid's maps suggest otherwise. The visible universe is the effect. The cause is something we cannot see. There is a technique Euclid also uses called baryon acoustic oscillations, and while the name sounds complicated, the idea behind it is actually quite beautiful. In the very early universe, long before any stars existed, when everything was an impossibly hot, dense plasma of energy and particles, there were pressure waves moving through that plasma. Like sound waves but on a cosmic scale. These waves traveled outward at close to the speed of light, pushing matter and energy in pulses through the early universe. Then, about 380,000 years after the Big Bang, the universe cooled just enough for atoms to form for the first time. When that happened, the plasma became transparent, the pressure waves froze in place, and the pattern they had been creating became locked into the distribution of matter across the universe. Today, billions of years later, that frozen pattern is still visible as a slight preference for galaxies to be separated by a specific distance, about 500 million light-years. It is a standard ruler that we can use to measure cosmic distances with precision. Euclid measures this pattern across enormous volumes of space. It tracks how that characteristic separation has changed over cosmic time. And from those measurements, it can calculate how the expansion of the universe has evolved, and therefore, how dark energy has behaved over billions of years. This is where things get interesting. The standard model of cosmology assumes that dark energy is a constant, a fixed property of space itself that has been pushing the universe apart at the same rate since it first became dominant. It has a name, the cosmological constant. And for the past few decades, it has fit the data well enough. But Euclid's early results are showing hints, subtle but persistent hints, that dark energy may not be constant. There are suggestions in the data that the expansion rate of the universe may have varied over time in ways that a truly constant dark energy would not produce. The signal is not yet definitive. The measurements need to be refined. More data needs to come in. But the whisper is there. If it is confirmed, if dark energy is evolving over time, then one of the most fundamental assumptions in modern physics would need to be revised. The cosmological constant would need to be replaced with something more dynamic, more complex, more interesting. And that would open up an entirely new set of questions. What is driving the change? Is it a field that evolves like other fields in physics? Is it related to something we do not yet know about? Could the future of the universe be different from what our current models predict? These are not small questions. These are the kinds of questions that rewrite textbooks.